Okay, start the recording, and I will end it at the end of the talk so that we can have questions in a private way. It's my pleasure to welcome you to the Monday seminar. I'm very excited because today we have Ivan Dokmanić joining us from Basel University in Switzerland. As you know, this part of the introduction is super informal. I wrote many things about the great work that Ivan is doing, and I invite you to look at that for some background about, especially his academic background and trajectory to this point. And if you didn't get that, if you'd like to join the seminar announcements, I'll post in the chat about how to do that soon. The normal operation is to ask people to mute during the presentation, but to invite you to jump in with points of clarification, some minor point that can help Ivan, I don't know, feel like he's not all by himself. There are many of us here. So, but at the end, we'll have a nice long question answer discussion period. So, save your substantial questions until after that. But we really would love everybody to participate in that. So if it helps you, especially early career scientists, I can recommend to you that you just make some notes about your question. Ivan, thank you very much for organizing this, and I'll turn the floor over to you.
Great. Thank you very much, Chris. It's really a privilege to be able to give a talk to this crowd. Now, it's no secret that I'm not an earth scientist. I'm not an earthquake scientist or a seismologist. My background is in electrical engineering and signal processing. So that's what I do. I also recently do a lot of machine learning. I work on algorithms and theory. And so, regardless of that, I always like to stay close to real data, real problems, to hardware, to signals. And so somehow, I was privileged or very lucky that I found some people who were patient enough with me to explain to me how beautiful seismic signal processing is. So in particular, a couple of years ago, well, more than a couple now, I started interacting with Martin Behop, who is a mathematician, but he works on many real applied problems with data in earth science and planetary science. And so Martin was kind of grooming me or mentoring me and explaining me patiently many things about inverse problems in seismology and also seismic data processing. Much more recently, I also started interacting with Chris on a couple of projects. And so I want to thank Chris for also, lending me his kind of experience. That's been absolutely great. So they showed me the beauty of this treasure trove of absolutely amazing and really important signal processing problems that are real. Now, Chris wrote in the email that something like Ivan Dokmanić invented some foundation model. Actually, I didn't invent anything. All the important work here was done primarily by two of my brilliant PhD students, Cheng Shi, who is still with me in the lab, and Tian Lin, who moved on to DeepMind. And we received enormous help also from two grad students of Chris, Laura Laurenti and Giulio Poggiali. And I should also mention Yanis Minimaier, who is here and who helped us a lot with understanding SeisBench and building the foundation model. I'll give a shout out when it's due. Right. So when I started, learning about earth science and seismology, which is late in my life, I was actually surprised to learn how little we knew about the structure of the Earth until quite recently. I mean, in the beginning of the 20th century, we knew more about the solar system, and we even had experimental confirmations to an extent of general relativity, but we had no clue that the Earth has layered structure, or we didn't know about plate tectonics. Okay, so I'm telling you things that you already know, but it somehow that somehow motivated me to think about why seismology has advanced so fast. And I want to talk about, so this is actually anti-causal. I basically want to talk about two things today. The first one is related to a foundational signal processing task, which is called phase association, which I guess most of you know about. And that's really not so much AI. It's really signal processing and careful machine learning to solve an important problem. And the second part is then really about foundation models. So it's more zeitgeisty about using huge amounts of data and really large models to extract performance that was not we just couldn't have before, right? So I go back to the narrative that I started, right? So somehow up until the mid 20th century, we didn't even know about plate tectonics. Things started changing right about then. So actually, Croatian meteorologist Andrija Mohorovičić, by analyzing seismic recordings from a local earthquake, figured out that there must be this continuity in material properties between the crust and the mantle that today we call Moho discontinuity. I suppose that this is because nobody outside the Balkans can pronounce Mohorovičić. And then things started, kind of moving, but slowly. So we learned about, for example, inner core from the work of a brilliant Danish seismologist, because then it already existed, seismology, Inge Lehmann. But plate tectonics, for example, was not, it was not a mainstream theory until the 50s or even the 60s, right? So although Alfred Wegener, who was a German meteorologist, proposed this theory of continental drift back in 1912, it took a long, long time, and a lot of insights on paleomagnetism, and then actually on cartography. So Marie Tharp was one of the brilliant cartographers who actually produced this wonderful map of ocean bottom, seabed, that was sort of a smoking gun, together with these insights from paleomagnetism. And I know that everyone here knows this much better than me, but I just found that fascinating because really, I thought that we had this planet under our feet for such a long time as a civilization and a species, and that we didn't know that it has a layer structure or plate tectonics, and we knew so much things about spaces. I found it kind of strange, right? But really, the observations that we have about the planet are very indirect. And so one thing that's my interpretation why this community has advanced so fast is that very early on, seismologists realized how important it is to share data and to curate data and to put it online. Well, not back in the 60s, but today. And so it's really a data-driven field, and it's really that's a great thing for signal processors and machine learners like me. Now today, I guess one of the main frontiers in this area is understanding earthquake dynamics, understanding earthquake physics more broadly, and this fundamental signal processing task in doing this and input is the ability to detect and localize earthquakes, and then estimate their properties of earthquake sources, be it big earthquakes or small earthquakes. And so the way this is done, of course, today is, we have these networks of seismic stations all around the world. We have global networks like Global Seismographic Network, and then local and regional ones. For example, in Switzerland, we have an excellent network. And these networks, these instruments are continuously recording seismic data and actually nearly instantaneously putting it online. You can download it. Now, I was presenting some of this material at a scientific machine learning conference a couple of weeks ago, and then I made a couple of slides to basically explain why, what is so interesting for me in working in this, right? And also somehow what I try to explain to my PhD students. So a couple of years ago, I was kind of very privileged. Well, actually, I'm very grateful to Martin for taking me. This is in Costa Rica. So we were going to visit some of the sites where you have instruments, and to get to these places, it's actually not trivial. You need a good car, and then you need to drive through the rainforest, and then if things go well, you get to a place like this on top of some hill overlooking the ocean, and this is what the things look like. Well, of course, you can't see the seismometer because it's buried, but there's the GNSS station. This guy here is Marino Proti. He's like a rock star of Costa Rican seismology. And we were really privileged, again, to have him be basically our tour guide. And see, one thing he explained is that when you're opening these cabinets that have some batteries, etc., communication electronics, that you have to be careful because sometimes there's snakes inside and then they jump at you. So when we were training neural nets with my students, and then something wouldn't train for weeks. We were trying, to tune training, learning rates, dropout, all sorts of kind of hackish things. At some point, we realized that some of the data that we worked with, some of these seismic traces, were just clamped to some nonsensical values, so they were just garbage. And then I always go back to this picture when I try to explain to people that this is real engineering and real science. So you shouldn't be surprised that that sometimes things don't look so beautiful. But that's also the appeal, I think, of the whole thing for me. Okay. Right. So if things go well, this is from the FazeNet paper by Zhu and Beroza, and I'll be coming back to this paper. If things go well, then at a single station you measure You measure something that looks like this. So this is an arrival and a P and an S arrival. Again, I'm preaching to the choir, but I'll just do the intro. So here the yellow lines, they're actually the detection of the onset of the P arrival, and the blue lines that take the S arrival. Right? And here, there's some labels. I'll try to explain these things a little better. Right? So this is an event that was detected, and now you'd like to localize this event and estimate its parameters so that you can do some downstream science. Now, of course, to do that, you need more than one station and more than one detection. And so, regionally, we have many stations here, these white diamonds, the different stations. And the way then you want to localize this event is by basically doing some sort of glorified trilateration. However, when you have a seismic array, you have many stations and you detect arrivals, data can look something like this, right? So here we have different kinds of P phases and S phases, so disks and squares. And a priori, you just, your phase picking algorithm just gives you a bunch of phase picks, and maybe labels are P phases or S phases, right? And so in order to localize events, now you have to figure out which one of these disks and squares actually correspond to the same event. And in this particular example, that's extremely hard because there are many arrivals. And it's not, so even this very foundational task, localize an earthquake, becomes very hard. This is an extreme example. So what you would like to get is something that looks like this. You'd like to get this color-coded thing where different colors correspond, they label different events, and each color corresponds to one event. This situation is quite extreme. This is actually doctored data, and I'll explain in which way it's doctored. It's realistic, but it's not real, because the arrival rate here is very high. The arrivals are extremely dense. You can see that, here we have some, this is 5 seconds, right? So between here and here, it's 5 seconds. So that's outrageously high. Okay. But this is a regime that's actually very interested in. Okay, so more pictorially, the problem looks like this, right? You have an event, which is this red star. You have 4 stations, the blue squares, and you detect arrivals. But when there are multiple events, then, this is what you have. And you can see that, for example, the yellow event here, corresponding to the yellow star, it arrives at the first station as the last event, but at the second station as the first event. So it's easy to come up with these examples where even the ordinal number of arrival carries no information, right? So the problem, you really have to somehow use physics in order to understand how to do the association. Okay, so this is what we have a priori. So existing phase association algorithms, the way they work is essentially, most of them work by backpropagation. So it's, in some sense, as I said, glorified trilateration. You try to find the source in the interior such that if waves emanate from that source, the arrivals at the stations are consistent with what you measure. And the way you actually do that is by backpropagating arrivals from the stations back inside the subsurface. That can be done in different ways. So there are grid search-based algorithms like real or PyOcto, which is extremely efficient because it's doing this grid search very, in kind of by subdividing the space in a very efficient way. We also have deep learning approaches like PhaseLink or Gini, which is based on graph neural nets, which actually just learn from labeled data. And then we have something in between, an algorithm that's called Gamma, which casts the problem as unsupervised clustering. So you have a bunch of arrivals, and you want to cluster these arrivals according to the events. So there's a way to combine that with some priors that are physics-based, and cast this as a problem of learning a Gaussian mixture model. Now, what are the challenges? Okay, so the challenges with association, maybe one of the main challenges is noise. Right? So your phase detection algorithms are imperfect. Sometimes they detect picks that are not real, they're spurious, they're noise. Sometimes they miss some picks. Sometimes some events are only detected at a subset of stations. And sometimes you detect events that are outside of your region of interest. So, then you cannot actually associate or localize them. And something that is, so this actual problem is the one that is addressed extremely well by existing algorithms. In particular, we worked a lot with Gamma, and the filtering algorithms and procedures in Gamma are just outstanding. And so that's actually something that we build on. The second problem is the problem of rate. It turns out that the current association algorithms, some of them can work at what we call high rates. But the max that they can achieve is about a couple of events per minute, which is something that we've seen, for example, in 2019 Ridgecrest sequence. But even at that rate, most of them buckle. And then if you go higher with rates, they start making a lot of mistakes. And the third challenge, well, there are many others, but these are the ones that I'm interested in, is wave speed variability. So if as I said, these backpropagation-based algorithms, they try to kind of propagate the waves back inside a subsurface and find consistent points of intersection. But in order to do that, you have to assume that you know the background wave speed model. And this is typically not the case. So what then these algorithms do is they either assume that the background wave speed is either constant, homogeneous, or that it varies in a simple way. For example, it varies just along the depth coordinate. And this turns out to work for reasons that I'll explain on the next slide. But rate and wave speed variability are in particular two challenges that we're trying to address with HARPA, which is the name of our algorithm. So I'll come back to that. Okay, so let's zoom in a little bit to this problem of wave speed variability. Right? So clearly, if the wave speed model is not homogeneous, your waves will, the rays will not be straight. And depending on, so for example, this couple of rays are almost straight, but this one here finds, a shortcut through this high wave speed region, right? And so it's quite bent. So if you assume a homogeneous wave speed model, you'll make a big mistake. Nonetheless, existing algorithms work quite well, all the while assuming simple, either homogeneous or this kind of waves 1D background models. And the reason they work quite well is that actually these approximations are not bad, depending on the rates that you're interested in and the depths. So a lot of times we're interested in relatively shallow earthquakes, and many sequences contain only shallow earthquakes, and also in relatively low rates. So this is an example from the 2014 Iquique earthquake in Chile, a sequence, and this here are minutes. So you see that here, sort of, even though we don't have the association, we only have a couple of events every 10 minutes or so. So the rate here is less than 1 event a minute. And so even by naked eye, it's not too hard to sort of figure out, even without any move out, just by the separation, by the large separation between the different events, what the correct association is. Okay, but this is not always the case. So okay, this is again the rate that we've seen roughly in Chile. Now, if you go to 2019 Ridgecrest and look for windows that contain higher rates of arrivals, then some windows will actually contain a couple of arrivals per minute, maybe like 2 or 3 arrivals per minute. This is what you see here. Now the problem is already a little bit more complicated because you see that you're starting to get some overlaps, so you have to play it smart. But you can think of increasing rates even further than that. And so here you have an arrival rate. So this is about 30 events per minute. Yeah, so this is really high. And so now here, the ordinal number of arrival doesn't play any role anymore. Right? You really have to use the physics correctly in order to perform association. A different way to see that, I wonder if I can use annotation. Okay, great, that works. Okay, so here, so this here is an example, just a synthetic example. Here we have a linearly varying wave speed just in the depth coordinate. And so it's not constant. So if you sort stations by the distance from the event, then you see that these arrivals line up. These are not straight lines. There's some curvature, but you see that this is a fairly simple situation. This is for 3 events per minute. Okay, so you get these orderly arrivals. Okay. Now, in this case, if you increase the rate to 30 events per minute, still you get, even though there is some curvature, still kind of these arrivals are neatly ordered. Okay, you can figure things out just by understanding the wave speed model. However, now we have synthetic wave speed models that are inhomogeneous, and the level of inhomogeneity is, or the amount is increasing. And so here, all the way on the right, you see that if your background wave speed is quite inhomogeneous, then actually these things are becoming little clouds. right? So there is no, there's no nice, neat rule anymore that you can exploit for association, and things start arriving topsy-turvy at the stations. And unless you know the background wave speed model, you'll be making big mistakes at this rate of 30 events per minute, which could be maybe, reached first at its, peak rate. All right. So let me trash that, clear all drawings. Okay, so why do we care about associating at higher rates? So I took some quotes from papers. So this is from Pari-Beroza and elsewhere. Micro-earthquake activity can eliminate otherwise unknown faults, particularly when events are detected down to low magnitudes and are located precisely. So you can find, all sorts of quotes like that, about, being able to track medium properties, earthquake-related properties, kind of 4D in real time at very high resolution, and understand earthquake dynamics to the level at which we currently cannot do with current earthquake rates. Now, from Gutenberg-Richter, we know that these events do exist at high rates, even when we only detect lower rates events. However, current phase detection algorithms, cannot, kind of buckle under the level of noise and difficulty in detecting these high rate events. But if we could do that in places like Yellowstone, or for volcano monitoring, geothermal energy sources, and even so I don't know if this is a good example because I'm not a seismologist, right? But even what was going on now in Santorini, these earthquake swarms, right? So it would be great if we could really track these things in real time at very high resolution. And so this is why we want to go higher rate. It would really unlock new earthquake science if we could do it successfully. Okay, so what is our approach? Well, my student Cheng-Shi looked at this problem, and so this is the way he started reasoning, right? So all current algorithms are treating individual arrivals one by one, right? So they really face this combinatorial challenge where you have, let's say, you have these 4 events, the yellow one, the red one, the green one, and the blue one, and you try to associate them to arrivals. And the way this is done is implicitly by solving some combinatorial problem, right? Because you treat each arrival separately and you try to associate it correctly to an event. So what he said is, let's forget about individual arrivals. Let's rather model entire arrival sequences as probability distributions. Okay, and so instead of modeling these arrivals one by one, what he does is he says, no, I'll look at a window of data per station, and I'll model this window of data. Actually, I'll model the arrivals that I have in this window of data as a probability distribution over arrival times within a window. And this is a game changer. It's a game changer because now there's no more combinatorial problems to solve. The only thing that you have to match are probability distributions of arrivals. And this is exactly, abstractly what he does, right? So he says, I want to minimize the distance between the observed arrival probabilities, which is an empirical distribution. Okay, it's these things here, but converted into a probability distribution, and between the probability distribution of arrivals generated by my model. So what is the model? Well, the model here includes the source parameters, in particular source locations, and takeoff times. But because we want to address the high rate challenge, we also have to include the unknown background wave speed model, right? So his model also includes the unknown wave speed, and he actually tries to solve this by minimizing both over the source parameters and or the unknown background wave speed. And it's, of course, a hard problem, right? So the first question is, can this be solved at all mathematically? Is this a reasonable thing to try? It's some kind of wild, blind deconvolution problem. And so actually Martin, Jonas, Matti, and Teemu wrote a paper about it and proved that under relative loose conditions, this problem has a unique solution. Actually, you can recover both the unknown interior sources, including their unknown times, and the unknown metric or the unknown wave speed model from boundary data. Okay, so at least mathematically, we seem to be on somewhat firm ground. But then there are algorithmic challenges, right? So we know that the problem maybe has a unique solution, but how do we compute it, right? If we parameterize the wave speed on a grid, we're going to end up with a huge dimensionality of the optimization problem. Then we have the challenge of how to actually optimize this. Do we do gradient descent with respect to source parameters, with respect to wave speed parameters? That's gonna, this is gonna be too slow, and who's gonna write that code? And also there's a problem of local minima. This is not a comics problem, right? Just because we pass the probability distributions doesn't mean that somehow now our problem has a unique minimum, a unique local minimum. Actually, there's a whole lot of local minima. And if you just try to run vanilla gradient descent, even if you're smart about differentiation and dimensionality, you're gonna get stuck in one of these local minima. So we have to deal with that. So the first problem of dimensionality, and actually to an extent the second one, the way we address that is by actually building generative models for families of wave speeds that look realistic and actually quite complicated. So in particular, Chang generated a family of wave speeds, and then he trained an autoencoder to embed this wave speed family that is realistic in a low-dimensional latent space. The same way you would train autoencoders for something else. This idea of using autoencoders for in the context of phase dissociation to parameterize families of wave speeds has actually appeared before, in particular in the PhD work of Hope Jasperson, Martin's former grad student. Actually, she had this really creative, stylish idea of using reinforcement learning to solve the phase dissociation problem, and we actually work on it together. I hope that actually I'm pretty convinced that that's a good idea. At some point, we should revisit it. But actually, what we're really interested in are not the wave speeds themselves, but are the travel times for any point in the interior to a set of stations at the boundary. And so actually what we do is for these wave speeds, we compute the corresponding travel time maps, which we call neural fields, because we can, not just us, but everyone else, because we can evaluate them for any interior point. And so actually we train generative models for travel times. We train these generative neural fields for families of wave speeds, where we at once parameterize travel times for a whole family of wave speeds to a set of boundary points. I should also point out that these ideas of using neural fields to parameterize travel times that's also appeared, for example, in the work from the group of Zach Ross. We probably know about ICONET and also in the context of phase dissociation. The main difference here is that we do not assume that we know the background wave speed. We have an entire family, and there's a family parameter that we're trying to identify. All right. So the last challenge is how do we actually optimize the parameters of this giant optimization problem where we're trying to find both the wave speed and the sort of parameters, and which is not convex. So simple approaches don't work. And so for that, we use an existing algorithm which is just kind of perfectly matched to this problem, which is called stochastic gradient Langevin dynamics. I'm happy to discuss why it's perfectly matched in the discussion, but essentially this algorithm combines Langevin dynamics with some kind of Monte Carlo sampling. So there's two sources of stochasticity, and it turns out that if you just use Monte Carlo, it'll be too slow. If you just use stochastic gradient descent, you're gonna get stuck. We actually have experiments that show that. And so somehow this is just a perfect combination, which guarantees that you're going to discover the correct global solution. Right? So that's pretty good. Okay, so let me show you quickly some results. So we've seen this before. This is the rate that we have in Chile 2014. Oops, this is the rate from Ridgecrest, and this is something that we create by hand. I'll tell you how, but it's a higher rate. So this is about 0.3 events per minute, 3 events per minute, 30 events per minute. Here are some association results. So maybe this plot here is the one to look at. This plot shows how many events actually we associate. And we compare different algorithms. Ours is HARPA, and then we compare it with the gamma, pi octo, real, and you can forget about this confusion factor. Right? So we're interested in the percentage of events found as a function of the rate. And we have a way to vary this rate kind of continuously, again, between 0.3 events per minute, which is about the rate that we've seen in Chile, all the way up to hundreds of events per minute. And you can see that initially at rates of up to maybe 3 events per minute, all algorithms perform about equally well. They detect a lot of events. Right? At this point, the combinatorial explosion, once you're getting more and more events within a window of data, this combinatorial explosion really starts hurting algorithms that are performing a grid search. Right? So there's much more, the space grows exponentially, and so actually the runtime starts killing them. Gamma performs exceptionally well, all the way up to the rates of maybe 10 events per minute, but then also starts to buckle under the load of the combinatorial load. But you can see that HARPA performs association nearly correctly, all the way up to rates of, really, really high. So hundreds of rates, hundreds of events per minute. Actually, it doesn't suffer almost at all from very high rates. Okay, so that's really the benefit of passing to probability distributions. Now, this example here is we still assume that the background is constant, that the background wave speed is constant. We didn't turn on this capability to search for the unknown background wave speed. Okay, so this is a setting which, in some sense, is a fair comparison between the different algorithms. Here is an example of what happens as we are making the wave speed more and more complicated. So we compare different algorithms. I'll try to guide you through this. Clear all drawings for wave speed models of different complexity. Now here we have two different rates, 3 events per minute and 30 events per minute. You can see that at this higher rate of 30 events per minute, even for a simple background wave speed, which is a linear gradient only in the depth coordinate, HARPA, which are the blue algorithms, starts associating, already associates many more events than other algorithms. So just like the sheer rate of 30 events per minute is a lot. Okay, but you see that when we pass to really, really complicated background wave speeds, then actually HARPA performs much better than all the other events. And I want to just spend 30 seconds explaining what these different bars are, right, for HARPA. So in particular, in order to be able to learn or nail the background wave speed, we have to train the saw encoder. We have to train it on a family of wave speeds, which we assume is somewhat realistic and hopefully plausibly contains the actual target model, right? But it's a bit unfair if we train on a distribution that we know contains the right models. So we test this in 2 different ways. We test it in distribution, where HARPA is actually trained on wave speed models that have this kind of elliptical inclusions. But then we also train it on some out of distribution data, which is Gaussian random fields, which is completely different. It looks nothing like this, okay? And kind of the encouraging thing is that even though, of course, as expected, when we train in distribution, we perform the best, even the out of distribution version of HARPA performs pretty well, right? So you can actually have like a huge mismatch, but the ability to adjust a little bit of this wave speed helps a lot. And then, of course, combined together with this probabilistic modeling of RILES. All right. So here's another example. You can ask, are these, are the parameters of earthquakes, so locations in particular, and also the wave speed that we discover, any good? And so here's another synthetic example where, we actually, just for illustration purposes, we have this outrageous dynamic range of wave speeds, which is not quite realistic. But we train again on these Gaussian random fields, which don't look like this, right? And we have 2 different association scenarios. One is with 8 events and 20 stations, and the other one is with 16 events and 50 stations. And as you can see, so here, for example, this here is a misassociation because the interior and this disk and the boundary have different color. But here, almost everything is correctly associated, right? But not only that, but actually, if you look at the parameters of earthquakes, the locations, they're pretty accurate. I mean, I would say extremely accurate compared to other algorithms. And also, this is the error in the wave speed recovery that we get. So you see that the color bar here is much smaller than the dynamic range here. So actually, we get kind of a decent initial estimate of the background wave speed model. And I'll come back to that. Okay, so I need to trash this again. Okay, so just to summarize this part, what makes this work? Well, there are 3 main ingredients, right? The first ingredient is that we use a probabilistic modeling of arrivals. We don't model them individually, but we just lift them into a probability distribution, and then everything else happens in the space of probability distributions. We use distances between probabilities, optimal transport, and so on. The second ingredient is that we use generative models for wave speeds and travel times that allow us to optimize efficiently our unknown wave speed models. And the third really, really important ingredient, it doesn't work without it, is that we use a very special flavor of stochastic optimization, such that we don't get stuck in local minima. We can solve this problem efficiently. All right. Okay, so that's all great. I talked about rates that go up to hundreds of events per minute. Now the question is, how can we ever obtain these phases? right? I mean, what we have in Ridgecrest is, 2 or 3 events per minute. What we have in Chile is less than that. So how do we get higher rates? So the plots that I showed you that have very high arrival rates, the way we obtain these results is by manually densifying real data. Basically, we took real data from Ridgecrest, for example, and then we just cut and paste different portions of these waveforms consistently across stations, and we shifted them left and right. And this way we can obtain any target arrival rate that we want, while making sure that sort of the physics of wave propagation are not messed up. Right? And this is how we basically obtain those plots. We also tried something else that is somehow preferable, or that should be more realistic, which is that we tried lowering the detection threshold in FaceNet, such that we obtain more and more events. So here's the result. So you can see that, so here, as we progressively lower the threshold, we get more and more peaks, right? And then we measure how many events are associated by different algorithms. And you see that at some point, HARPA starts detecting a few hundred more events than other algorithms, which is a good thing, right? But the bad thing is that when you look at these associated events, it becomes clear that when we lower the threshold in FaceNet too much, we start detecting a lot of events that are, we get a lot of these detections that are not really prime quality, in the sense that, they're probably noisy peaks. Okay? And so even though we get a lot of good associations here, these associations, kind of pass all filters, right? So in some sense, HARPA is really honestly doing a good job here, in the sense that it does find an event with some parameters such that it generates waves that are consistent with all the detected arrivals. However, these detected arrivals are probably noisy, right? And so at this point, we're facing a challenge of improving our phase detection algorithms. There's maybe better versions of, FaceNet. I'm sure that people have trained it to detect this much more reliably, and I'm actually eager to hear about it. But this observation sort of motivated us to work on kind of this waveform level signal processing problems and work towards foundation models. Right, so okay, so let me say a few words about FaceNet, which is really I would say this is not the only deep learning based phase detection algorithm. There are others. We use FaceNet, so that's why I'm presenting it. But everything that I'll say somehow is also true for the other ones. I'd say this has been without exaggeration a small revolution in seismic data analysis. Right, prior to deep learning based phase picking, highly reliable phase picks could be obtained basically only by manual work. Right, so people were manually labeling waveforms, and they created these massive catalogs that could then be used to train deep learning algorithms. So FaceNet in particular has been trained on 30 years of observation and manually labeled data. Right? So that's kind of human work that went into training FaceNet. Once it was trained, Jules and Berosa demonstrated that it actually is as reliable as human annotators, and this meant that you can now create massive catalogs. Right? So this really generated this deluge of data, of picks that now has to be associated. Right? That's absolutely amazing. But at the same time, we've seen that when if we really want to detect events at small magnitudes, then we need to push the performance further. Right? And so the way FaceNet is trained is via supervised learning. Supervised learning means that you have your waveforms. You wanna say whether your piece of data contains a P or an S arrival. And so you create a label, which in FaceNet is created in a very, very creative way by actually creating kind of a bump, a probability bump. And then you try to map your input, which is the waveform, to this label. And this is reminiscent a little bit of what, of the state of, let's say, computer vision and natural language processing in 2010s, where if you, for example, in text processing, you wanted to solve different tasks like text summarization or translation between languages, you actually created these labeled data sets. Okay, so for example, in text summarization, you had the summary and you had the text as input, and you were trying to map your text to the summary in a paired way. Okay, and this has worked pretty well. especially after the advent of deep learning. But a real revolution happened in the 2020s, which is that at some point someone realized that there's so much more unlabeled data. Okay, we cannot really have summaries for every piece of text that was ever written. There's a vast amount of text on the internet. And if we could find a way to leverage the text to build good representations, then maybe we could perform better. And this turned out to be true. Actually, the performance has increased a lot. And the name of the game is self-supervised pre-training. Right? So you can use this massive amount of text or images on the internet. You just have to invent some task, which is often called a pretext task. And then you're doing self-supervised learning such that you can learn some representations, which you later then fine-tune on a specific task, like summarization. Okay. So we try to do the same in the seismic context. So here's what a general self-supervised learning strategy looks like. It's always some sort of a filling in the blank task, right? You have a bunch of text. You want to learn a good representation of text. You don't have any specific labels. There's no specific task. So what you do is you just, you mask pieces of text. You put them in a big neural net, typically a transformer network, and you ask this neural net to predict what was in the blank. And you're trying to do well on this task, just filling in the blank. Okay? And so Tianlin, this is actually a slide made by Tianlin. So what he realized is that this is actually reminiscent of how people learn language. If you ever tried Duolingo, then it'll give you these little quizzes where it'll ask you to fill in the blank. Someone est français, right? Elle est française. So actually, humans learn very much the same way. And you have the same kind of paradigm for image processing. So something called masked autoencoders are trained such that they try to predict the missing pieces of an image via a transformer. So like the image is first split into these little blocks. It's tokenized. So you find some kind of discrete units of representation for these blocks. You go in the transformer and you try to predict the missing pieces. Same thing for speech, and this is actually what we build on. It's kind of very similar to seismic data. Again, you kind of mask pieces of speech and you try to predict units of speech from the missing ones using a transformer network. And just kind of a parenthesis, this paradigm is now proliferated far out of computer vision and natural language processing. So for example, in scientific machine learning, people are now training foundation models for physics, for partial differential equations. They're trying to train transformers, for example, to do time stepping or forecasting for complex flows, diffusion advection, Navier-Stokes, whatever, tens and tens of different PDEs. They learn this simulated data, and then they bring a new problem, and then they show that they can actually learn to forecast a new phenomenon much faster with only a few labels using this pre-trained model for physics. This has been done also at the level of Earth. Aurora is a model that came out of Microsoft Research. They model not just the weather data, but they model all sources, whatever is available and supported on the planet. And they also show that this enables actually very, very fast transfer to new tasks. Okay. So, what are the three key ingredients that you need in order to make any such foundation model works? I think, different people will have different favorites, different three ingredients. But my take is that what you really need is you really need data, data, and data, right? And so people will disagree. They'll say models are really important, and I will agree with them in the sense that, before transformers, we didn't have such models, so we couldn't take advantage of huge amounts of data, and transformers scale exceptionally well with large data sets. However, for most domains now, the bottleneck is not models. Now, we have these transformers, we have all of these architectures online, and betters will be invented. But the point is that if you work in a domain, like, for example, seismology, where people have been diligent and careful enough to curate the data sets, to make them easy to access, then you'll be able to train these models, and otherwise you won't. Someone needs to do this work. Okay, so as I said, seismology is very blessed in this sense. It's both data rich and data driven. There are curated data sets online. So in particular, we could not train our seismic foundation model without there being SizeBench before. This is what we use. Okay, so SizeBench, you probably, everyone knows about SizeBench. It's a suite of tools for seismic signal processing and data analysis, but in particular, it includes data loaders and data sets, okay, from a whole bunch of sources. Some are listed here. And so actually, I have to say thank you to Janis Münchmeyer, who helped us actually work with SeisBench and train a foundation model. We could not do it without it. It would just be impossible. We actually tried on some other data without using SeisBench, and we failed. So that's how important it is. So what is the model that we use? It's fairly standard. Okay, so it's really inspired by Wave2Vec2, which is used for speech. And we make a couple of modifications to Wave2Vec2. But really, I mean, the backbone of the model is the same. So this model consists of something that's fairly standard that most models have, which is a convolutional feature extractor. They're just like a filter bank that we also use traditionally in data, in signal processing. Now, this extracts, a bank of convolutional features, which are then quantized and fed into a transformer, right? So we kind of convert these convolutional features or filtered waveforms into some discrete units of representation, and we then just we train this by using again a mass prediction task, right? So we try to basically we try to predict the middle token from everything else, right? These are the construction targets, okay? And yeah, this is done using discrete tokens. So this is very important because it simplifies the architecture. We can train it using a classifier loss instead of doing some sort of crazy contrastive learning. But this is all well known in the community, and it also acts as a regularization, right? So none of this we invented. We really just took a model, we adapted it to our data. Right. And so you start training this thing to predict pieces of waveform from other pieces of waveform, and you realize that this problem is damn hard, right? So if you're used to, like I was, to training, let's say, image classifiers and ImageNet, you're used to seeing the laws go from some kind of random guessing performance to 99.5% accuracy, right? So here we train two models, what we call a base model that has 11 million parameters, and a large model that has 90 million parameters. We train these models for a week or 10 days on 4 big GPUs. And after a week of training, your loss goes down from whatever, 3.9 to 2.6. Now, when Tianlin showed me this, I thought it just didn't train. This thing doesn't work. Your loss decreased by 0.3 on a scale of 4. This is not training. Nothing is happening. But in fact, to decrease this loss, this prediction loss from 3.9 to 2.6 is outstandingly difficult. Because the task is, just the task is difficult, right? So this is what the data looks like. This is again from the PhaseNet paper. And this is just to show you the variability that you have to deal with. Like, first of all, the task basically boils down to predicting pieces of this waveform, like, for example, the middle part from the rest. Now you see that there's all sorts of, this is like high frequency, there's noise, there's everything. This is fundamentally a complicated thing, right? You cannot really do well in this task. Not only that, but actually this is a different example from a data set that PhaseNet was trained on, that we trained on. This is just two different kinds of sensors, right? And you can see that qualitatively, you're trying to solve a prediction task for waveforms that look completely different, right? So in some sense, this is a hard task. And being able to do a little bit better than random on this actually means a lot. It means that you're learning a lot about the structure of your data. Okay, so here's one example of performance. I'm not gonna bother you too much. You can go to our workshop paper, look at it. But this is the problem of phase identification. So the task here is you get a window of 30 seconds of data of seismic waveform, and you have to decide whether there is a P or an S arrival in the middle of it. And so we try this on different seismic data sets. Okay, so basically we use the exact same setting as in the PhaseNet paper. And the first thing that you see is that, well, SeisLM large performs the best on every problem. Even here, but the dynamic range is not big enough to see it clearly. Now I should explain, what the abscissa here means, right? And now, because we have so much unlabeled data that we trained it with, what we try to do is we try to see how different algorithms behave when we really reduce the number of labels, right? So we go from the usual number of labels that's used to train PhaseNet, for example, to only 5% of those labels. And what you see then is that size LM large kind of, it deteriorates a little bit, but not much. But supervised algorithms deteriorate a lot, right? And that's incredibly important, because if you now go to a new region, to a new, to a new array, to a new planet, whatever, it means that maybe you only need a handful of labels to start bootstrapping your data analysis, right? Maybe 5%, which is much easier to obtain than hundreds of thousands of labels that you need to train from scratch. So that's exciting. Another example that I really like, and I have to say thank you to Laura and to Chris for that, it has to do with classifying foreshocks and aftershocks. Actually, the setting is really the same as in their recent NatureCom paper, probing the evolution of faults during an earthquake cycle. And so the data comes from the Amatrice-Visonorcha earthquake sequence in 2016. Okay, so I'm trying not to butcher this because Chris is looking at me, but basically the idea is that there's been a main shock, and so a couple of months before that there were foreshocks, and after that there were aftershocks. Okay, that's just like my very naive way to describe it. Now what you can do is you can try to take an arrival or detection that is a foreshock or that is an aftershock, and you can try to build a classifier that decides, that tries to predict whether a piece of waveform is a foreshock or an aftershock. You can actually make the problem even harder by splitting this period here into bins, in particular, for example, into 4 different bins, 1, 2, 3, 4. So you have 4 classes of foreshocks that are distinguished by their distance to the main shock, and you also have 4 classes of aftershocks, right? It's pretty exciting. I mean, if you can do well on this problem, it means that you really learned something about the evolution of, fault properties during an earthquake cycle. And so here are some results. Okay, so this is a convolutional network like the one that was trained by Laura, and I really want to emphasize that this here is just an incredibly exciting level of performance, right? So baseline, so this is 9 classes, okay, and so if you just guess randomly, you'll have an accuracy of about 10%, right? So what Laura did is she trained a convolutional neural net that achieves accuracy of about 60%. So this is much better than random. If you look at this confusion matrix, I mean, you're right most of the time, or you're close to the diagonal, right? So you're really doing well. Okay, so we basically took, Laura's setup that was extremely valuable. So, she taught us how to use her data. And this is what we get by our base model. So this is seismic ALM base, and it improves performance to something like around 65%. And the large model gets accuracy of almost 75%, 74%, okay? So that's now beyond exciting, because you really, look at the confusion matrix. We are, in some cases, we're right like 99% of the time. And actually, in the meanwhile, we further improve this model so we can achieve performance of around 80% of this task, right? And we basically never make mistakes that are far away from the diagonal of the confusion matrix. We keep working on this. So that's great. So now I want to share some closing thoughts. Maybe for the first time, when we train these foundation models, I think this was the first time in my research career that I had something that works extremely well, and I really didn't understand it. Like, I didn't know why. I couldn't pinpoint, this is why it works well. And in particular, it was counterintuitive to me, because if you think about PhaseNet that was trained on, hundreds of thousands of detections from California, this is a setting that in machine learning is just perfect. You have a big model, very expressive. You have a ton of data, and you're solving a supervised learning problem. So the theory of empirical risk minimization tells you that at some point, you will approach the performance of the best classifier, which is the best possible. So then it was totally counterintuitive to me that a foundation model that's trained on data outside California, for some reason, performs better than PhaseNet on California, which was trained only on that data. And not a little bit of it, but a lot of it, right? So this is a perfect setting in some sense. This shouldn't happen. It's counterintuitive. And I was thinking about a way to explain this to myself so that I can start doing some theory about it, and hopefully an explanation that also makes sense to you. So the explanation has to do with wine, or at least my intuition. And I think wine is really it's really a great thing to care about, right? Culturally, it teaches you about culture, about history, organoleptically, in all sorts of ways, right? So you can imagine that, you're like blessed and you've been born into this town of Montalcino in Tuscany. And so all your life, you've been drinking Brunello. And you know, it's like you understand that this is way above standard, way above average. And you're eating good food, you're drinking good wine, and you know, you don't complain, right? You understand that you're privileged. But at some point in your life, someone gives you a bottle of great Burgundy, and you drink it, and you think, wow, I mean, you're mind blown, right? What is this? You know, what is this crazy wine, right? You realize that, I mean, there's all this other stuff out there that you haven't tried. Someone gives you a bottle of, you know, Bordeaux, a Spanish wine. Someone gives you a bottle from New Zealand, and your mind is blown, right? So then you realize that, you know, this Brunello is just a point in a giant coordinate system, right? You know, this dried cranberry that you were picking up in Brunello, you realize this is just a value of a coordinate along an entire dimension of red fruit, right? And that, you know, crushed violet is just a value of coordinate along an entire dimension of floral notes, and tilled soil is just, you know, it's just a value of coordinate along an entire dimension of earthy notes. And so now at this point, not only does your general appreciation of wine and gastronomy improve, but actually your understanding of Brunello, which is California, in the earthquake example, goes up, right? So not only do you understand all other wine better, but actually you understand Brunello much better, because you understand that it's just, you know, it's a part of this magnificent organoleptic universe, right? And so this kind of semi makes sense. At the same time, you should say, well, but ERM theory teaches us that we have all this data from California and great models. We should actually do better. This still doesn't make sense. So at this point, I think what that shows is that actually all the assumptions, the theoretical assumptions that we make in machine learning, like that the data is, for example, independent and identically distributed, that your probability distribution is always the same, it never changes, etc. Actually, all of these assumptions are not enacted in real seismic data. Okay, they're not true. So this is why foundation models work better. Okay, a few other closing thoughts. This is a typical email from Cheng. You know, this is 1:40. This is actually early in the night for him. He says, "Dear Martin, and even I guess I found some structure beneath Chile, and I find it somewhat convincing, as different distributions of wave speed models converge to similar results." Okay, so this is this is what happened when Cheng applied HARPA to, you know, the Chile data set, and then he actually enabled learning the background wave speed. So, or various different generative models of wave speed, he was consistently discovering something at, you know, 100 kilometers depth and more. So we checked the literature, and sure enough, you know, this is consistent with the increased wave speed due to the subducting slab of this Nazca plate, right? And, you know, we checked this many, many times over, and it seems very convincing. Now, the exciting thing about it is that this is typically not how you see wave speed variations at those depths. Typically, you use, you know, more complicated and you know, more complicated procedures and more data. So I think that what we've done with HARPA, passing to these probability distributions and looking at the problem, you know, in a completely different way, I'm pretty sure that this actually can be pushed to problems that are not seismic phase association. I think we can actually start doing inverse problems with it. And, you know, I invite you to try out both HARPA and SeisLM. They're online. In particular, HARPA is very easy to install. You know, you just pip install. It's part of SeisBench now, or it uses the SeisBench interface, so you can easily apply to your association problems. You can also try out SeisLM, and if you need help, let us know. And so finally, I want to underscore this. Like, there would be no SeisLM without SeisBench, right? So it's really important that someone in the community does this effort of organizing data. So this is not just SeisBench, it's all the data curation that happened prior to it and that kind of fed into it. And then SeisBench with the interfaces. Scaling laws are important. Large models work better. That's a bit annoying, but it's true. Somehow we can actually make use of much larger data sets when you have larger models. And so it's the first time maybe in my career when I believe that sometimes it does make sense to train huge models. And finally, you know, our initial plan was to model a day of seismic data. Actually more. We had this kind of crazy dreams. You're going to model a month or whatever. That turned out to be completely impossible with current architectures, with current, transformer models, etc. We settled on 30 seconds. That seems to work. With more compute, we could do a bit more. But currently, we are not modeling earthquake dynamics, right? We're modeling snippets of seismic data. It's great pre-processing. It feeds into many other algorithms. I think it's a game changer, but we're thinking hard on how to actually make this work for days of data. So that's all I have. Thank you.
Wow, fabulous. I will invite people to unmute, turn on their camera. Join me in thanking Yvonne for really a fabulous talk.
Sure. Thank you. Yeah. It's great to have the opportunity.
Yeah. Okay, and now I'm going to kill the recording to make it clear that